All right, this is Math 1, Unit 5, Geometric Sequences. This is going to be the notes that you're going to be taking today, so pay attention to the video. If it moves too fast, you could always go back. It'll be downloaded on Google Classroom and on YouTube. Okay? All right, so the first thing is, when we talk about geometric sequences, we need to first figure out what exactly is a geometric sequence. Okay, so what I'm going to do is I am going to give an example of 4 sequences. Okay, so these are 4 examples of sequences. Now, some of the examples will be considered geometric. Some of the examples will not be considered geometric. Okay, so number 1, and remember, if you forgot what a sequence is just a list of numbers. All right, so a sequence is just a list of numbers, and typically there is some type of pattern or order that the sequences follow. For instance, 3, 6, 12, 24, 48, 96, and so on and so on. Remember that dot, 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 that is actually called an ellipse, and that just means that the list of numbers is continuing. Okay? All right, so that would be an example of a sequence. Here's another example of a sequence. 1, 6, 11, 16, 21, 26, 31, and so on. Okay, dot, dot, dot. That means the list keeps going. As I'm writing these sequences, you should be looking at them, and some of you probably intuitively, which means in your mind, and because you have good math sense, are saying you know what I'm doing in order to get from one number to the next number to the next number. All right, here's another example of a geometric, or I'm sorry, of a sequence. Some of them, once again, are going to be geometric. Some of them are not going to be geometric. 800, 200, 50, and then the next one's going to be a decimal, and that's okay. 12.5, and the next one's going to be a decimal as well, and that's okay, and it's going to be 3.125, and comma, and then so on and so forth. Okay, and then the last one here, let's do one more that would be considered a sequence, and a sequence is just a list of numbers, and they typically follow some type of a pattern. Okay, how about 6, then negative 12, then positive 24, then negative 48, then positive 96, and so on and so forth. Okay, so all 4 of these are examples of sequences. Okay, now here's how you tell if it's a geometric sequence, and this is what we're focusing on today. So today our focus is on what is a geometric sequence, how do you know a sequence is geometric, and once we know that it is, what are some of the common terms that we're going to see, and what are some of the formulas that we're going to have to know if something is a geometric sequence. Okay? Now, a geometric sequence is, by definition, it's a sequence that it's a sequence of numbers, so it's a list of numbers where the next number is always being generated by multiplication or division. Okay, so a geometric sequence is a sequence of numbers where each term is being generated by multiplication of the previous term. Okay, of the previous term. All right, so if we looked at number 1 right here, you could see we started at 3, then we went to 6, then we went to 12, 24, 48, 96. So in these problems, we're increasing by value. So every time we go from one number, and each number we call a term, by the way. So 3 would be called the first term, 6 would be called the second term, 12 would be called the third term, and so on. So each time I go from one term to the next term, I'm increasing in value. Okay, now, am I increasing in value by the same amount? And some of you are probably saying yes. Kylie Delk right now is probably going, yeah, of course. Lauren Linford is probably thinking, but she's never going to say anything, but she's thinking, yeah, Mr. Trutna, if I want to get from 3 to 6, that means I'm multiplying by 2. If I move from 6 to 12, that means I'm multiplying by 2. To move from 12 to 24, that means I'm multiplying by 2. Okay, to get from 24 to 48, that means I'm multiplying by 2. Okay, to get from 48 to 96, that means I'm multiplying by 2. Emily Caldwell, sit down. At this point, you don't need to be walking around. And Ryan, stop talking. For goodness sakes alive, come on. Let's stay with it here. Vielka, you too, stop talking for a second. Pay attention. Okay, thank you very much, Yuriana, for listening. And Kenny, stop making some weird noises. Okay, so anyhow, because that I am multiplying by 2 to get to eat from one term to the next term, let's read the definition. Okay, so a geometric sequence is a sequence of numbers where each term is being generated by multiplication of the previous term. Notice I am multiplying, so in number 1, this is an example of a geometric sequence. All right, and that's how we tell. So multiplication tells us, that's the clue. All right, you guys, if you're generating numbers by multiplication, that means that you have a geometric sequence. Okay, so in number 2, you can see I started at 1, I went up to 6, then I went from 6, then I turned it into 11, 11 became 16, 16 became 21, and so on. All right, so you could see this is a sequence because there is a pattern being developed, but if you notice, what's the pattern? Well, I'm adding by 5. So 1 plus 5 gives me 6. 6 plus 5 gives me 11. 11 plus 5 gives me 16, and so on. Okay, you guys, so because I'm doing addition in this problem, this would be not geometric. Okay, so number 2 is not a geometric sequence. All right, now number 2 has a name. We studied it last semester, but we're only talking about geometric sequences today, so let's not worry about the name. Okay, taking a look at number 3 right here, I have 800. I went down to 200. 200 went down to 50. 50 went down to 12.5. 12.5 went down to 3.125. So I'm decreasing in value. Okay, so what's the pattern that I'm using in order to decrease? Okay, well, there's only 2 ways to make numbers decrease. I could either subtract, or I could divide, or I could do the opposite of divide, which is multiply by a fraction. Okay, now some people would say, oh, Mr. Trutna, this is super easy. To get from 800 to 200, you divided by 4. To get from 200 to 50, you divided by 4. To get to 50 to 12.5, you divided by 4. So you look, if I did a calculator right here, 50 divided by 4 is 12.5. 12.5 divided by 4 is 3.125. So we are dividing by 4. Okay, but here's the problem. A geometric sequence involves multiplication, not division. So the question is this sequence in number 3 geometric? The answer is yes, it is geometric. So number 3 is a geometric sequence. Why is it a geometric sequence, Tyler? Thomas? Okay, thank you. Because when you divide by 4, as you probably just heard Tyler Thomas say, and I'm pretty sure that Hayden said it also, it's the same thing as multiplying by 1/4. So if you multiplied 800 by 1/4, that would give you 200. If you multiplied 200 by 1/4, that would turn it into 50. So you guys, so you have to think of geometric sequences not as division but by multiplication. And it's easy. If you're dividing by 4, that's the equivalent of multiplying by 1/4. So that's why that one was a geometric sequence. Okay? Number 4, the last example that we're going to talk about, if something is geometric or not geometric. Notice we went from 6 to -12. Well, what's a way to get from 6 to -12? What? I can't hear you. Ashlyn, what did you say? Good, Ashlyn Rice got it right. She said you multiply by -2. I think Kylie Lopez said that too. Sorry, Kylie, I couldn't hear you. Yeah, you would multiply by -2. 6 times -2 is -12. Okay, so let's see if that pattern stays the same. So if I took -12 and I multiplied it by -2, is -12 times -2 positive 24? Sam, you are correct. It is positive 24. Okay, good. Then if I took 24 and I multiplied it by -2, is 24 times -2 -48? What do you think? Ricky Reed, what do you think? Oh, it is -48. So we're multiplying by -2. Okay, and then the last one here, if I took -48 and I multiplied it by -2, Rana, would that equal 96? Yeah, you're right. So if you guys notice, I'm multiplying the previous term to always generate the next term by -2. So is this problem a geometric sequence? The answer is yes. Number 4 would be an example of a geometric sequence. Okay, so one of your questions that you're going to have to be able to answer is, are sequences geometric? Hopefully you figure that out right now. Remember, the key is to make a sequence geometric. There has to be a pattern on how we're always generating the next number, and the pattern has to be developed by multiplication. Okay, so we have that. So that would be our first step in understanding geometric sequences. Okay, now let's go ahead and let's understand our second step to geometric sequences. So what I'm going to do is I'm going to write a geometric sequence down. Okay, 2, 4, 6, 8. You can continue it if you want to. Wait, what did you say? What? I can't hear you, Kai. Oh, that's not a geometric sequence because you're adding by 2. Very good. I tried to trick you there. Kaylee Manriquez, you should have figured that out right there. Yeah, that is not a geometric sequence. So now let me write down a geometric sequence. How about 2, then 4. I'm going to be multiplying by 2. So what's my next number, Elise Ward? 8. That was good. Wonderful. Yeah, 8. Naali, what would my next number be? 16. Good. Dylan, what would my next number be? 32. Good. Dylan, remember to pick up all the garbage on the floor when you leave. Okay, and then if I wanted to keep going, I would have 64, 128, and so on. Okay, so this right here, hopefully we all agree, this would be an example of a geometric sequence. Okay, now when we talk about a geometric sequence, there are 2 formulas that pertain to a geometric sequence. All right, there is a formula which we call the explicit formula, spelled E-X-P-L-I-C-T. Okay, we have an explicit formula. And go ahead and write this down. You're going to have to be familiar with this formula. The explicit formula is A with a subscript of n is equal to A with a subscript of 1, then times the multiplication symbol for the dot times R and then to the power of n minus 1. Okay? And then there's another formula, and the other formula is known as the recursive formula. And the recursive formula, and you want to write this down as well. Ricardo, wake up, write this stuff down, would be a subscript of 1 is equal to a, and then a with a subscript of n is equal to a with a subscript of n minus 1 times r. Okay, now both of these formulas have lots of variables in them. They have lots of letters in them, and what we want to do is we want to see what do the letters in the formulas mean. Some of the letters we're not going to worry about. We're never going to change them, but some of the letters will always be turned into numbers. Okay, so in these formulas, the a subscript 1, that means the first term, okay, which we'll call the starting value. So in the formula, the a subscript 1 stands for the starting value, okay? That would be your first term that you have, or the first number. So the first number in this sequence would be 2, okay? R, the letter R in both of the formulas, notice there's a letter R in both of the formulas, it stands for the common ratio. Okay? Now the common ratio is what are you multiplying by? Okay, so it's the amount that is being multiplied. I guess we could say that. Probably not the best way to put it, but I'm a math teacher and not an English teacher, okay? Speaking of that, Kayla, stop reading a book right now, okay? Pay attention here. Reading makes you smart, and we don't want you to be that smart, okay? All right, so we've got that there. So so what we want to do is we want to say, all right, so if I have a sequence that's considered geometric, I can put that sequence, I could represent it in what's called an explicit formula and also in what is called a recursive formula. And let's go ahead and practice that, and I'll do it once here and we'll do it a second time, and then we'll call it a day, and then you guys could get to work on your assignment. All right, so the explicit formula. So what we do is when we have the explicit formula, you are going to put a number in the place of the a subscript 1 part. You are going to put a number in the place of the r part, and everything else in the formula you're going to leave exactly as it is. Okay, so what I mean by that is the a subscript n will stay a subscript n. The equal sign will stay an equal sign. Now the a subscript 1 is going to be your starting value, which is 2. So you're going to put a 2 for a subscript 1, then you're going to put a multiplication symbol, and then your r, you're going to put a number in for r. Your r is your common ratio. It's amount that is being multiplied by. Okay, so what am I multiplying 2 by to turn it into 4? Well, I'm multiplying by 2. Trevor, that was a great answer right there. Okay, am I multiplying 4 by 2 to turn it into 8? What do you think, Carla? Yeah, you're right, you are. And as a matter of fact, if you look at it right here, as Jackson just said, you're multiplying by 2 every single time, okay, to generate the next number in the list. So that means my r value is 2. So I'm going to turn r into 2. So I'm going to have 2 times 2, and then n and minus 1, those are going to stay exactly as it is. So that right there would be the explicit formula for this geometric sequence. Okay, now let's write the recursive formula. Okay, so now when you write the recursive formula, the recursive formula, first of all, is always going to have 2 lines. Okay, as the formula suggests. You are always going to put a number in the place of a subscript 1, and you are always going to put a number in the place of r. Okay, and everything else you're going to leave exactly as it is. Okay, so as Christian just said, that was very good observation, Christian, that, wait, in either formula, the only thing you change is the A1 and the R spots of the formula. Absolutely, Megan Proust, that was good. Wonderful. Shannon Shields, do you agree? Yeah, I agree too. Okay, so how do we write the recursive formula? Okay, I'm going to put a number in for a sub 1. Well, what is a sub 1? It's the starting value. What's the starting value? It is 2. So I'm going to write 2. I put an equal sign. And then I put an A. Okay, so this is telling me I'm starting at 2. Then I'm going to write the second line of the formula. I put an A. I put a subscript 1. I don't change that. I don't change the equal sign. I don't change the A subscript of n minus 1. I keep the multiplication sign, and R is going to be my common ratio, which we already decided was multiplying by 2. So that right there would be my recursive formula for this geometric sequence. Jadia, you are absolutely right. You will always have 2 lines in the recursive formula. Okay? So that's going to be our lecture for today on geometric sequence. Math well and prosper.